we're going to start off with Newton's law of gravity. And the simplest way of explaining Newton's law of gravity is just saying that all mass attracts all other mass. Right? All mass attracts all other mass. That's the simplest way. Right? A couple of other things to point out is that attraction between two objects is always equal and opposite. So let's pretend that here this is the Earth. Mass 1 is the Earth, and M2 here is you. Right? You know you have a certain weight, a certain force between you and the Earth. And so let's say it's 180 pounds. Earth pulls you down with 180 pounds. Right? Newton's law of gravity says that you also pull on the Earth, and it's equal and opposite. So Earth pulls you down with 180 pounds. That means you also pull the Earth up with 180 pounds. The Earth is so massive, you're not going to notice any effect of that, but you are trying to pull the center of the mass up towards you. Okay. Here's Newton's law written out in algebra. And if you like equations and this makes sense to you, you can skip the next little bit of lecture while I try to explain it in words. But if math makes you nervous, all right, we'll do it in words. All right, we're going to first explore the effect of the mass. What happens if you change the mass? How does it change the force? And then we're going to look at how does the distance between them affect the amount of force. And notice that the distance down here is squared. So it's going to really affect the amount of force between them. So let's just look at the amount of mass. So here we just start off with two masses. Mass and a mass, they're identical. And the amount of force that each of them are pulling towards each other is just going to be called F, a certain amount of force. Okay. If you double one of the masses, so we're going to go from this top one now to the second one. If you double one mass, what that does is it doubles the force. So if you want to go back and look at the equation, you can kind of imagine how that works. But just remember, if you double one mass, you double the force. We can take that a little bit further and go from here down to here. If you triple one mass, you triple the force. Right. If you're ready for it, what happens if you double both masses? If you double both masses, you have to take into account that effect twice. So you don't just double the force, you end up quadrupling the force. Right. Taking into account a change in distance is a little bit more complicated because of that r squared. Whatever change in the distance you do, you have to take it into account twice. You have to square that change. So here's our initial situation. A mass, and a certain distance. And they'll be attracting each other with a certain amount of force. Right, so let's take that initial distance and double it. Double that initial distance and leaving everything else the same. Because they got further apart, gravity between them is going to get weaker. But by how much? You change the distance by 2, well, let's square it. 2 times 2 is 4. It's going to get weaker by 4. So that's this 1/4 F. It's going to get weaker by 4. Instead of moving objects further apart, you could move them closer together. That's down here. From that initial case, let's move them twice as close together. Let's half the distance. And because you're bringing the masses closer together, their gravity will affect each other more strongly. And so gravity between them, the force between them, will get stronger. but it'll get stronger not by a factor of 2, but by a factor of 4. Right, you have to take into account the distance change and then square it. Just kind of looking at this idea a little bit more, that distance is going to matter a lot. We've got 3 objects to keep track of here. We've got the Earth, we've got the Moon, and we've got a rocket. And these scales up here, the scale shows how much force is between the Earth and the rocket. And since the rocket right now is on Earth, the rocket feels a lot of gravity from Earth. And the Moon is very far away from the rocket, so the rocket feels very little force from the Moon. So as the rocket gets further from Earth, it'll start to feel less and less gravity from the Earth. And as the rocket gets closer and closer to the Moon, it will feel more and more gravity from the Moon. We're just kind of looking at how the distance affects it. Let's put the rocket smack dab right in the middle, right there. Right now the rocket is equal distance from the Earth and equal distance from the Moon, but it feels more gravity from the Earth than it does from the Moon. That is purely because the Earth is more massive. There's more gravity between this pair of objects, just because the mass of the Earth is bigger, than there is between this pair of objects. But we can change that overall balance by playing with the distances. Right about there is a special point called the Lagrange point, which probably isn't in your book at all. There's 5 Lagrange points around objects in space where gravity can balance out in really strange ways. And right there, the rocket feels equal gravity from the Moon and from the Earth. So if you were to release something right there, like say a communication satellite, it would hover right there and it wouldn't fall either way. It's balanced. And just finish off, put the rocket back on the Moon. Alright, let's get into orbit. And we'll just start off with what an orbit is. Start off with Newton's original thought experiment. He thought of a cannon on a mountain and what would happen if you shot the cannon out at different speeds. So let's start off just firing the cannon, and the cannonball shoots out and eventually hits the Earth. Gravity pulls the cannonball down and it'll slam into the surface of the Earth. And Newton was thinking about this and he said, I wonder what would happen if you could shoot the cannonball faster. Oh, it went further around the Earth. And what if we could shoot the cannonball even faster? The cannonball is falling the whole time, but making it further and further around the Earth. And this is what led Newton to think about orbits, is if you were to find the exact right speed, that the cannonball would fall around the Earth, but the rate that it would fall is perfectly matched to the curvature of the Earth. So that cannonball is always falling. So I could also say it's always weightless. Nothing's supporting it. It's always free falling. It's just that its speed is perfect that it will always miss the surface of the Earth, and you get a circular orbit. For the space station, it takes about 85, technically 88, I think, for the space station. 88 minutes for the space station to go around one time. So think about the astronauts up there. They have a morning every 88 minutes. It's going to really mess with your internal clock. Let's change the mass, because maybe it's not a cannonball anymore. What if it's a space station? Right? Let's up the mass and reload the cannon. How will it affect it if we change the mass of that object? No change. As long as that orbiting object is tiny compared to Earth, the mass has no effect. The mass has no effect. It's really the speed. The speed is what determines the orbit. Too slow. Whoops. Boom. Just right. Circular orbit. The mass of the cannonball didn't matter at all. And let's find out what happens if you go too fast. Just a little bit too fast. You get an elliptical orbit. So remember from your readings that a circular orbit is a special type of an ellipse, but this is an ellipse with some eccentricity. This orbit is a little bit longer, and it takes a little bit longer to go around. If you were to go a little bit even faster, you'll get an even more eccentric ellipse. Take even longer to orbit. Remember Kepler's third law? The bigger the semi-major axis, the longer it takes to orbit. Newton came up with it again, it just now he's able to talk about it in a different way. A little bit faster. If you go too fast, the cannonball will escape into space, never to return. Whereas Kepler said that orbits have to be elliptical, which includes circles, right? Newton's going to go one step further. Now that he has the law of gravity, he can determine that there are different types of orbits. You can still have the elliptical or circular orbit, and that's called bound. But you can also have unbound orbit, which basically means your object is going to escape. If your speed is exactly the escape speed, that's this, you would end up traveling on a parabola. And if you go even faster than escape speed, you would end up traveling on a hyperbola. Don't worry about the details there too much, but just know that Newton broadened what we thought was possible by discovering the law of gravity. Newton now allows for unbound orbits, so the object never comes back. Okay. An orbit itself is stable, assuming that there's going to be no energy. Right? Orbits are stable, right? And in order to change an orbit, you have to change its energy. So the Earth keeps on its orbit, the same orbit every year. If you wanted to change Earth's orbit, you would have to change Earth's orbital energy. So you can either put ginormous rockets on the back of Earth, or if there was some a nebula out in space, some gas, that would create a drag and slow us down. Starting over. Orbits are typically stable, and if you're going to change an orbit of an object, you have to change its energy. So let's say here you have Earth, and you already have a spaceship orbiting Earth. You've already done the launch, you're already in an orbit around Earth, and let's say you want to get that spaceship further out. Maybe so that way it would match Mars or the Moon. What you have to do is you have to change that spacecraft's energy. In this case, you want to go to a bigger orbit, so you're going to need to add energy to it. So you could have rocket engines. But if you want to change an orbit, you have to change the object's energy. Orbits do not spontaneously change all on their own. Alright, we're going to work our way into talking about Newton's version of Kepler's third law, which is going to turn out to be important. But before we jump into that, let's go back and remember Kepler's third law. Okay. Kepler's third law says that the larger the orbit is, the longer it takes to go around. Right? And this was measured in AU, astronomical units, and this was measured in Earth years. Sorry about my writing there. The bigger the orbit, the longer it takes to go around. And Kepler's third law worked for anything orbiting the sun. So the major planets, asteroids, and comets, but only things going around our sun. And now that Newton has discovered the universal law of gravity, he's going to be able to generalize this so it works for any pair of orbiting objects. Right? So, Newton's version of Kepler's third law. Let's go through this a little slowly. And it doesn't have its own special name. That's literally what we call it. Newton's version of Kepler's third law. Right? And he's going to keep what Kepler said, that a larger orbit takes longer to go around, but now it also depends on the total mass of the two objects. So it's more general now. You can use it for any two objects, and it depends on the total mass of the two orbiting objects. And so there's more mass, there's more gravity, they're going to end up orbiting faster. Okay. And so why this is important to astronomers is this is actually how we measure masses of different distant objects. Okay. So if you look at this, it's algebra, but this constant here, don't worry about it, it's just a constant you plug in. There's three other things in here: the time per orbit, total mass, and semi-major axis. So what the algebra says is if you can find two of those things, algebra will tell you the third. So usually how we do it is we look up into space and find an orbit, and we study the semi-major axis, we observe that, and we can observe how long an orbit takes out in space. And what it does is if you can find those two things, it lets you, with algebra, calculate the total mass of those two objects. So this is a huge deal in astronomy. We can calculate the mass of a galaxy if we can find something orbiting it. We can calculate the mass of a planet if we can find a moon going around it. We can calculate the mass of a star if it has a binary companion. Right? We've never been out there with a scale, but we know its mass. And that has let us be able to understand a lot of stuff out in space. Right? Right. So it lets you find the total mass of both objects. But what if you just want the mass of one object? Right? Then you're going to be looking for a lopsided pair. So let me show you this next animation to kind of go through this last bullet point. Right? Let's adjust this and start out like this. Okay. Let's say you wanted to know the mass of that central big star. You want to know the mass of this big star. So you use Newton's version of Kepler's third law, and you observe how long it takes this little star to go around once. You just wait. There you go. use a stopwatch, find out how long it takes for an orbit. You use your telescope and you figure out the size of the orbit, the semi-major axis. Right? Using those two things, Newton's version of Kepler's third law will let you determine the mass of both of them together. The mass of the big central star and the mass of that tiny star out there. But if you rounded, if that's an obviously lopsided pair, that big central star is much more massive, we astronomers will round and just kind of say, well, let's just say we found the mass of the big star because the mass of that other one is tiny. We'll just ignore it. Right? There is more math you could do to really separate it out, but we're just going to say we found the mass of that big central object. Right? I can play with this a little bit more and show you that mass can affect how long it takes for things to orbit. So here both of them are very low mass, and notice that they're orbiting very slowly. There's less gravity, there's less speed. Let's crank them both up to high mass, lots of gravity. They're orbiting each other very quickly. All right. That's basically what this version of the law is telling you. The more mass there is, the faster it'll go around. Alright, let me decrease the mass of that central star now, and you can watch the orbit slow down. Right, the orbit slows down. Right, the more gravity there is, the faster objects tend to go around. Tides. We close this chapter with tides. And a tidal force is basically a stretching force. And the stretching is just going to it's just due to the fact that part of the Earth is closer to the moon than the other part of the Earth. So if you look here, this part of the ocean is closer to the moon, so this part of the ocean feels more pull from the moon's gravity, so it'll bulge out on the front. The back part of the ocean is further from the moon, so it feels the least amount of gravity from the moon. Right? And then that's the stretching. Part of the Earth is pulled more than the other part, and it stretches. It stretches, and that is shown in the Earth by the tides. The weird thing is if Earth's ocean is only pulled more strongly on the front side here, why is there a tidal bulge on the back? Why does the ocean bulge out on the back side, where there's even less gravity? I like to explain it best by noticing that the center of the Earth was also pulled by the moon's gravity. So what you should actually think about is that the Earth used to be more to the left in this figure, and that because of the moon's gravity, the center of the Earth shifted a little bit to the right, leaving that back bulge behind. So this is actually a bulge left back here kind of by inertia. It's not bulging out because there's something back there pulling on it. It was just left behind. It wasn't pulled as strongly by gravity. If you were to just ask the Earth how it felt, it's a little anthropomorphic, but if you were to ask the Earth how it felt, it would compare it from its center of mass, and from its center of mass it would feel as if it was getting stretched on both sides. Right. So the upper panel here is what's happening. The lower panel is what it would feel like from the Earth's point of view.